So electrostatic interactions occur between electric charges. And there are three basic types of such interactions. The first one is called ionic or charge-charge interaction, and it occurs between full charges. For example, we have here an ammonium molecule interacting with the negative anion of formic acid. The second type is an interaction between a full charge and a dipole. A dipole forms when two atoms that are connected by a chemical bond have different electronegativities. So the atom with the higher electronegativity draws some of the electrons of the bond towards it and becomes partially negatively charged. And therefore, the other atom, which has a deficiency of electrons, become partially positively charged. And the example that we have here is of the same ammonium molecule interacting this time with the hydroxyl group, which is a dipole. And in this dipole, the oxygen is partially negative and the hydrogen is partially positive. And finally, we have an interaction between two dipoles. And the example that we have here is the ammonia molecule in which there is a dipole interacting with the same hydroxyl group that we saw above. So let's start with the ionic interaction. And as I said, it occurs between full charges, like the ammonium molecule and the formic acid, the charged formic acid molecule. And this type of interaction can be both attractive or repulsive. It depends on the signs of the two charges. If the two charges have opposite signs, like in this case, the interaction is attractive and the energy of the interaction is negative. However, if the two charges have the same sign, if both of them are positive or negative, the interaction is repulsive. They are repelled from one another, and the energy of the interaction is positive. If we consider the two interacting atoms to be point charges, we can calculate the energy of the ionic interaction between them by using Coulomb's law, which is these equations that we can see here. So in the case that we have here, for example, when we have 2 point charges, Qi, Qj, and the distance between them is Rij, the energy, according to Coulomb's law, the energy equals the first charge multiplied by the second charge and divided by the distance r between the two charges, and divided also by a second factor called the dielectric constant, which is noted by the Greek letter epsilon. And I'll explain in a moment what it means. I just say that this is a property of the medium in which the charges reside. So Coulomb's law shows us that the energy of the ionic interaction is greater as the charges are bigger in terms of their magnitude, and the distance between them is shorter. And it also gives us the sign of the interaction, whether this interaction is attractive or repulsive. For example, if Qi has a -1 charge and Qj has a +1 charge, then the entire expression will be negative and the energy will be negative. And when the energy is negative, it means that the interaction is attractive. If the two charges have the same sign, then the expression in the Coulomb equation will be positive, and a positive energy means that the interaction is repulsive. If we want to get the energy in kilocalories per mole, which is usually what biochemists prefer, we should use charge units of electron charges, 1, 2, 3, and so on. The distance should be in angstroms, and we should multiply the entire expression by 332, which is a prefactor that gives us the energy in kilocalories per mole. Last thing to mention is that the ionic interaction is considered to be long range, and maybe right now it doesn't make a lot of sense, but when we'll talk about interaction between dipoles, we'll see that they are much shorter range. So the Coulomb equation is pretty simple, but we haven't understood yet what epsilon means, what the dielectric constant means. I mentioned that it has to do with the property of the medium in which the charges reside, and it actually expresses the ability of the medium to mask or to decrease the strength of the interaction, of the ionic interaction between ions inside this medium. So what makes the medium mask interaction or decrease their magnitude, their interaction energy? This has to do with the polarity of the molecules that compose the medium. We saw earlier that some molecules contain polar bonds, which makes them dipoles, and such molecules are said to be polar molecules. The more polar a molecule is, when it composes a medium, it allows this medium to mask the electrostatic interactions inside it more efficiently. And we can see here, we can see this in the example here of sodium and chloride. Sodium has a +1 charge, chloride has a -1 charge, and for simplicity, we can consider the distance between them as 1 angstrom. Now we can imagine that these two atoms can be in 3 types of media. The first one is vacuum. Vacuum does not have anything inside it except the interaction charges. So the dielectric of the medium is 1 because it doesn't have any polar molecules inside it. So in this case, the energy is very simple to calculate. It's 1 times 1 divided by 1 and 1 times 332. And we get that the energy is 332 kilocalories per mole, which is very large. It should be minus 332 because this is an attractive interaction. The second case is oil. Oil, as we'll see in a moment, is composed of molecules that are not polar. Their polarity is very, very low. And so the dielectric constant is also low, it's only 2. And in this case, the energy is 332 divided by the epsilon, which is 2. So the energy is minus 166 kilocalories per mole. The energy is half of what we have, of what it is in a vacuum. And the third case is when the charges are in water. Water is a very polar medium. We'll see that in the next slide. And its dielectric constant is therefore 80, very high. And since the dielectric constant is in the denominator of the Coulomb equation, the energy is 332 divided by 80, which is only 4 kilocalories per mole. So we can see that the more polar the medium is, the interaction energy is lower. And this is because the medium is composed of molecules that can mask the electrostatic interaction. To understand how polar media like water can mask ionic interactions inside them, we should look at the individual molecules composing such media. And here we can see the single water molecule on the left, and we can appreciate that this molecule is very polar, and it is polar for 2 reasons. First of all, it contains 2 oxygen-hydrogen bonds. Each of them is a dipole. It is polar. And it is polar because, as we discussed earlier, the oxygen is more electronegative than the hydrogen, so the electrons of the bond tend to be mainly around the oxygen, and it has a partial negative charge. The hydrogen, therefore, has a partial positive charge. We can express the polarity of this dipole by using this equation, which gives us the dipole moment. The dipole moment is the separation of the 2 partial charges along the bond, and it's a way to express the polarity of the dipole. And it tells us that the moment is the charges times the length of the bond that separates them. It assumes that both both partial charges have the same magnitude, which is not exactly right, but it's an approximation. You can also see that the dipole moment has a direction, and it points always from the negative side to the positive side. The units of the dipole moment are Coulomb meter, but it is usually more convenient to use the Debye unit, which is a Coulomb meter multiplied by this factor. So the first reason for the polarity of the water molecule is that each of these oxygen-hydrogen dipoles is polar. But moreover, there are two of them, two such dipoles, and both of them face the same direction, which create a situation where the hydrogens face one side and the oxygen faces the opposite side. So if we look at the entire molecule, this side of the molecule is positively charged, partially but still, and this side is partially negatively charged. And what we have here is a molecular dipole, which is greater than each of these micro dipoles. On the right, we have an opposite example of a nonpolar molecule, methane, which creates a nonpolar bulk medium. And this molecule is nonpolar for two reasons. The first is that it is composed of four carbon-hydrogen bonds, and each of them is nonpolar. It is nonpolar because the carbon and the hydrogen have very similar electronegativities, so the bond electrons are almost evenly distributed between the two atoms, and there is no polarity. But even if each of these bonds was to be polar, these polarities would be canceled out because each of the bonds faces a different direction. So in any case, such a molecule would not be polar, and the medium composed of this molecule is also nonpolar, and it cannot mask electrostatic interactions. How does the fact that each of the water molecules is polar allows the entire medium to mask the electrostatic interactions inside it? To understand that, let's look at this image. We can see the two full charges, positive and negative, embedded inside the water medium. And the medium is composed of separate water molecules. And we can see that these molecules are arranged in space in a way that allows each of them to interact with other water molecules in a way that stabilizes the entire system. This interaction, which is called a hydrogen bond, we'll talk about it later, is between the oxygen atoms of water and hydrogen atoms of other water molecules. And it is made possible because, as we saw earlier, the oxygen and the hydrogens have opposite partial charges. Now, we can see that most of the water molecules form hydrogen bonds with one another. But, for example, if we look at this part of the image, we can see that the full positive charge is surrounded by water molecules that do not form full hydrogen bonds with one another. Instead, their oxygen atoms surround the full positive charge. They face it, and their partial negative charges interact with this positive charge. On the other side, we have the full negative charge, and there we see the opposite. Some of the water molecules surrounding the negative charge interact electrostatically with this charge via their hydrogen atoms, which have positive partial positive charges. So what happens here overall is that both full charges are masked by their interactions with surrounding water molecules here and here. And as a result, the ionic interaction between the two full charges is much weaker. And this is the molecular basis for the masking phenomenon that I talked about. Now, the interaction of each of the full charges with its environment, which in this case includes the water molecules, the energy of this interaction can be calculated by using the Born model. This model assumes, for simplicity, that each of the full charges is a sphere that has a charge q and a radius of r. And then we can calculate this energy, which we call the polarization energy, by using this equation. You can see that the equation is a derivation of the Coulomb equation, and it equals the charge square divided by 2 epsilon r. And remember that, again, that r in this case is not the distance between the two charges, it's the radius of each of the charges. And again, if we want to get the energy in units of kilocalories per mole, we multiply it by this prefactor. So we can calculate the polarization energy using the equation, but one of the important implication of it is that it allows us to calculate also the transfer energy of the full charge from one medium to another. And to do that, we rearrange the equation so it takes into account the dielectric constants of the two media. And this is the final equation. And this type of calculation is important because when we focus on biological systems, we often see compartments inside organisms that have different dielectric constants, different polarities. For example, we have high dielectric compartments like the cytoplasm inside cells, like physiological fluids, blood, urine, the lymph, and so on. And we have low dielectric compartments like the plasma membrane that surrounds each cell, the inner membrane inside the organelles in eukaryotic cells, and the brain-blood barrier. So it's often important for us to be able to calculate how much energy we need to transfer a charged molecule from one compartment to another. And if we take, for example, a simple transfer from of a full charge with the +1 magnitude from water to oil, to remind you, water has a dielectric of 80 and oil has a dielectric of 2. This transfer, if we assume that the distance between the two charges is 1.6 angstrom, this charge, according to the equation, this transfer costs us 50 calories per mole, which is a lot of energy. And it expresses the notion that charges prefer to be inside polar media and not to be transferred into low dielectric or lipid media. Each of the two types of electrostatic interactions that we just encountered are also important in when we have charges within large molecules like proteins or DNA or RNA and so on. And we can see here an example. We can see a protein. We just only the surface of the protein is visible, and the protein is surrounded by water molecules. And we have two point charges on the surface of the proteins. The charges are noted schematically as a minus and plus signs. These are full charges. And these two charges, although they are a bit distant from one another, they can still feel one another, so to speak, via the Coulomb interaction between them. But if we look at one of the positive charge, we can see that it is also in the vicinity of some of the water molecules that surround the protein. And in this case, we have the polarization interactions between this full charge on the surface of the protein and the partial charges that are on the water molecules surrounding the protein. So we have the two types of interactions in the context of a large molecule.